TUBS-IRMB. Digital India. Educated India.
One thing that you should know about forces is there is some academic intent, motivation to talk a lot about forcing. So people can invent forcing schemes for Lattice Boltzmann, write a paper, and then they got their paper, right? And this is how a lot of these things come into being. And this leads a little bit to the implication that doing the forcing in Lattice Boltzmann is extremely difficult. Yes, maybe a little, but not as much as it is implied by this. So, talking about forces, we should potentially try to understand that there is now I have to make something up. So if you look at our asymptotic analysis, where we get usually, say, we have the first moment here and over bar of first order plus dx m the second moment to equilibrium to second order plus dy, say we stay in 2 dimensions, m 1 not over bar or equilibrium to second order is plus you get these things now, the third moment equilibrium to first order, and this is probably 3 times this, and dy. Okay, I kind of forgot whether this is 1, 2, 1. Okay, so there are these things that I would have to look up myself, whether there's a 2. I think there's a 2, right? There's a 2. 1, 2 to first order equilibrium. So, and then comes this omega 1, 0 to third order, okay? So don't nail me down on these on these prefactors now, yeah? So the force comes here at the third order, right? So this means, I mean, this is the change in the first order moment, and this has to occur at third order. So in principle, this is relatively small. So imagine you have a small error in your forcing, yeah? So your forcing is not completely accurate. Then so say this is only first order accurate, yeah? So then you have a first order error in your force term, but then this becomes taken to the third power again, and so you'll have the error that you produce by using a slightly off force term will usually be small. For this reason, with all these different force terms that you have, it's actually very, very difficult to show that one is better than the other. Yeah? Because whatever force you put is already small, has already to be small. Yeah? And so the error that you do in the force also needs to be small, and then it is small again. So actually doing the very simple thing gives you almost the same result as doing something more complicated. Having that said this, there are cases where more accurate forces are important, and this is usually the case when you talk about some multi-phase models. Why is this the case in multi-phase models? So in multi-phase models, in particular in diffuse interface models, you have in a very, very thin bound interface where you have to put a very strong force. Yeah? And the interface actually becomes smaller. You make you're making the grid spacing smaller, also steeper. Which means that you are actually representing a singularity with a smoothed out version of with a smoothed out force. Yeah. And this singularity, because it's a singularity, it actually does not fulfill this asymptotic behavior. And in this case, the forces actually do not shrink with higher resolution, right? And there the forces are actually very strong. And there it actually makes a difference whether you use an inaccurate force or an accurate force. So if you do something simple like gravity, you basically don't care about the accuracy of your force. You can do something extremely stupid, it will do exactly the same, right? If you have a high density ratio multi-phase model where you need a force in the interface in order to approximate the to compensate for the errors in this interface, then it makes a difference. So then what should you do as a what should you do as a force? I mean, what is the problem with the force? So the problem with the force is that if you look, for example, at the equilibrium, and let's look at the moment M11, for example, right? 11, M11, for example, before collision, yeah, and for example also to second order, will have here the rho u v, all of this, so this would be to zero order to first order, minus 1 over omega, theta, right, 1 over omega theta dx v first order plus dy u first order. Okay, I'm making this up from my memory. I think there's a theta, yeah? I believe that there's a theta. So now, if your velocity is not accurate here, because this is the question, what would that be, right? So actually, this should be the average velocity. So the one that is in between the time step before and the time step after this, yeah? Which means that this u, for example, u average should be the sum of I f I j over I and j plus 1/2 the force in x direction. Yeah, this is. I mean, the force divided, say the force divided by rho. It should be the acceleration. Yeah. Okay, so this is also 1 over rho, right? So this is what it should be. Now, And this is also what these things like goo forcing basically do. The problem usually is that most of these methods start from the pre-collision state, yeah, and take the velocity at the pre-collision state. Now, if you apply everything, the collision in, or you compute your equilibrium from the pre-collision state, then you have here so the wrong equilibrium. Yeah, so this here is the equilibrium. So you actually have the wrong equilibrium you are using. And then you can derive correction terms for having this wrong equilibrium and add this correction terms, and then there's then the goo forcing. Yeah? So one other way this can be understood, and maybe this is not the most efficient way to implement it, even though I think that the goo forcing, I mean, making this error and then adding a correction term is also not an efficient way of doing things. Yeah, but one way, one other way, at least you can think about these things, is by looking at strung splitting. And now you have to remember that the reason why numerical methods may not be second order in time is because they are not symmetric. And the thing with if you do it like Gu did it, using the pre-collision state, yeah, so you're obviously not symmetric because you're applying the collision without the force to the pre-collision state, so you need a correction. So one way to make forcing second order accurate is to make also the forcing symmetric. And even though this doesn't need to be done in particular this kind of way, you can think about it the following. So we talked about strung splitting. Strung splitting, and in strung splitting what we did is we keep the collision, and we do one half streaming before and after. And this is related to our picture here where we have delta x and delta t, yeah, and we have here our nodes, yeah, and say we have here our collision, and we have here in between we have the streaming. And you can now easily see we do half a streaming here and just half a streaming before that, and then again the collision, and then again so there's this missing. And then we do half a streaming again, and then here a collision. So of course, doing half a collision and doing half a collision is something that you don't do in practice, yeah? Because it is just moving halfway and then moving halfway again, yeah? So, but now if another operator comes on top of this, you can actually add this to this procedure in order to keep this symmetric. So what you can do is you can either put one half of the force before and one half of the force after, or you can actually say we do one half streaming, one half of the force, then we collide, one half of the force, and then we stream again. So this is again symmetric in space and time, right? No, it is, sorry. Okay, this doesn't say anything about space. It only says something about time. So what you would actually have to do is you have to apply the force at the location in between the nodes, yeah, and at the time in between in between the collisions. What you can do is you do half streaming, force, and a collision, and force, and half streaming again. So this half streaming, you see this half streaming is again combined with another half streaming and the force and the collision before, and then the force again, and then again a half streaming. So you are still able to combine this to a full streaming, right? So now what you can do is you do a streaming, then you apply half the force, then you do the collision, then you apply half the force again, and then you do the rest of the streaming, and then you will be second order accurate in time, right? So if you are second order in space, depends on whether your force depends on space and how you implement this. And this is, so for example, a gravity force is usually not dependent on space, but if you implement a force on the boundary of a droplet, because they have a multi-phase flow, then you may want to have this very accurately spaced into space. And then you have to remember this is then not on the node, but it is in between the nodes in space. Okay, now how can this be done efficiently, in particular in the cumulant method or in central moment methods? So what we do if we compute either central moments or cumulants. So when we compute cumulants, we do this usually starting from central moments, right? And therefore, this is basically you're basically doing the same thing. So what's the procedure is that, say, you compute the this pre-collision central moment over I and j. You can I minus u and by the power of a and j minus v by the power of b if I j, right? So say this is pre-collision velocity, and then when you do the back transform, you can do this with the post-collision. So you'll have u star, so which is now the post-collision the post for, so this is the pre, or say pre-forcing, and this here is post-forcing, yeah, by the power of a and j minus v, after forcing by the power of b if I j, after, and this is of course after, yeah. So you take it before and you do the back transform later. This No. Okay, forget it. Not this way. Okay, cut this. Please cut this from the recording. You know, yeah. Okay, we do the other. We do following. We do the following. So we actually compute these things at half. Yes, we get these things at the intermediate steps. Yeah. So this is where we want to see them. Yeah. So this causes one problem, namely that the K10 is no longer 0. Yeah, because because this would only be 0 if the velocity would not have been forced. Now we compute them in the centered way. Yeah, but this Fij has not yet been forced. So what does this mean? We see that these guys, because they get forced, they are not 0, and they also have to change during the collision. So if we use U bar, the forward and the backward in the forward and the backward transform, yeah, they would not change the K10. Does this make any sense to you? So we do the same forward as backward transform, because both times we use the same U, which is the same velocity, which is the velocity at the collision time. Right? Then these things here actually have to change, and the way they have to change is that we say K10 after collision and by extension the streaming is minus K10. Yeah? And K02 after collision is minus K0, no, not 02, 01 is minus K01 before collision. So reason is because they were half the force away from the actual value. Yeah. So in order to get twice that, on top of it, we have to subtract their offset in order to get to the other side of this. So now what you do then is you basically get all the moments back as AB after collision is again, so you have this relationship, and you have to solve this for the Fij after collision, and the collision or forcing operator. So this is the forcing operator here. So this will give you something that is second order in time and should not produce here any first order stress. So I cannot guarantee you that this is the best solution for doing multi-phase flow. Yeah, but this is a pretty simple way to impose a force. And at least for simple forces like gravity, this should work. Okay. Any questions? Did this help at least somewhat? Please, but please use the microphone.
So here, U bar is.
So U bar. Wait, did I write U bar? Okay, maybe I have not written U bar. So U bar. Didn't I write U bar? I write U bar here.
So is it like in the first step and like pre-collision and post-collision, is it the same U bar?
Yeah, so you see pre-collision you mean here in the, you mean down here?
Yes, yes.
Yes, yeah, here it's the same.
So it's calculated from the pre-collision populations, right?
Yeah, it cannot be calculated from the pre-collision alone. So you can calculate it from, yes, so okay. So if you calculate it from the post-collision, you could also calculate it from the post-collision, but it's difficult to calculate anything from the post-collision because then you're already done. So this is 1/2 of fx. So this would be, you know, the one is the one needs to be added half the force, the other needs to be subtracted half the force. So this is at least a symmetric method in time, and therefore it's symmetric therefore it should be second order. Okay. Actually, we were supposed now to talk again about virtual fluids. And in that, an example where we use grid refinement. So obviously, Lattice Boltzmann virtual fluid uses grid refinement of the type that I've been explaining today. It also can use force of the kind that I was explaining a few minutes ago, where we simply, in the transformation, said the use the half forced transformation in the central moments. So the example we want to look at is basically this one here, where we have a cylinder, and we have domain that looks like this. So actually this is a common benchmark by Turek, yeah, where we study the flow around the cylinder, usually at Reynolds number 20, so it's pretty low. This morning I set it to 2000, and then I let it run for a few minutes and recognized that the velocity was low. So this is now just so starting to do something, yeah. So of course we would have to wait a little longer. Let me see whether I start the simulation here, but waiting for the simulation is because I use a lot of grids. Here maybe a little bit tedious. So let's just have a look. This example is not yet in the distribution. I complained to my colleagues that there is nothing where we actually read a VTK file. Yeah, all of these things were just using normal, primitive shapes. So virtual fluids can use a few primitive shapes like cylinders and spheres and boxes, and so on. They can be generated, but they can also use STL files. So STL files is a file format where you store objects in terms of triangles. Okay, so and this is here now implemented. So also is Konstantin Kutscher. It includes virtual fluids and also some other files here. It also uses, so first thing that it does, it again reads the configuration file. The configuration file is provided like here. So we have we can specify the location of the the geometry file, which is this cylinder file that is actually loaded. So this is this STL here. So you can load the STL file. I don't know whether you see this very properly. Also into ParaView. So this has been specified here, and then there's an output. And again, you can specify the threads. Now I put it to 8 because apparently I have 8 cores, not 4, I don't know. We specify the block size. So this is a bit, block sizes don't need to be squares. Yeah, so this has 26 times 42 times 42. Then originally the velocity was set to 0.001. If you want to have a good result, you should use small Mach number. Yeah, so this is actually required to get good converted result that conforms with literature. I put it a little bit higher, yeah, in order to get it, get a quicker result. So yes, so this is something I'm not going to talk about now. There is the possibility that you set this to false and reload, from a previous simulation, but then the previous simulation has to dump everything and in order to continue. Okay, then what we can also do is we can add more observers to the kernel, which we'll see. That calculate for here the CP value or something, yeah. So they measure forces on a body, and do this during the simulation, and then giving an output. Okay, and then the time steps, and here is NUBS steps. This is when they will compute the NUBS, so the node updates per second. Okay, so this is our configuration file. We can read these things. We always need an MPI communicator, and the root MPI process is doing all the writings out, yeah, so that we don't do this twice. So then some of the coefficients here are defined directly here. You can debate whether this is a good idea or whether they should be in the input file again. So usually I should do it this way. So the benchmark is actually on a Reynolds number 20 and not on a Reynolds number 2000. There is, because it's a benchmark, there is a real velocity that is 0.45 meters per second. There is, of course, a rho. There's a radius of the cylinder. And from all of this, you can compute the real viscosity, and all of this also has to be translated into a lattice Boltzmann velocities and viscosity. So the velocity is already given here. So it is already given at the input file. And here you just set now the viscosity according to this velocity and the size of this thing, and given the delta x. So delta x is now the grid spacing, and it's given at 0.01. And yes, so there's actually built-in unit conversion already to turn this into these units. Okay, one thing that looks a little bit strange, and we'll have this in the lecture tomorrow, so we'll only one lecture more, but this is one thing that comes up tomorrow, is that we set rho equal to 0. Yeah, and I told you that you should not put rho equal to 0, because then you divide by 0. The reason why we have this here is related to conditioning. So this is actually not the real rho. What he should have written here is it is the delta rho. So basically, this is supposed not to be rho order 0, but rho order 2. And this we initialize to 2. Rho order 0 is a constant. And because it's a constant, it makes more sense to actually get rid of this thing and don't store it at all. And this is how virtual fluids functions. It is not, the rho 0 is not stored here. So all the equations are modified that they work around rho equal to 0 without, dividing by 0. So you actually have to modify the equations for this a bit. Okay, then again we specify no slip boundary adapters. So we have a no slip BC to which we initialize, and we specify here this to a no slip interpolated, which uses again 1-point interpolation as a boundary strategy, which is the algorithm. We could also specify here that this is just simple BGK, in which case there would be no interpolation. But now we used it with interpolation. In this example, let me go maybe here. Surface. No, wait. Slice surface. Okay. So what you see as input here is actually not a constant inflow, but a parabolic inflow. This is how this benchmark is defined. Now, as I told you yesterday, we sometimes have to implement these parabolic profiles or other given profiles, and this we can do by using this function parser. So we generate here an object for this function, which we often call FCT. And for this, we have to specify the expression. And in this expression, we have here the velocity, and we have the velocity, the height of the channel, and we have some coordinates here. So the velocity and the height of the channel, they have to be given. So we have to define these as constants. I think this is similar to how you would do things in SymPy, for example, right? Yeah. So you have to specify what is U. So U is ULB and H is H. H is the height here of the channel, and then this function here will be applied. And inside this function, there are already these coordinates. So these don't need to be specified because they are automatically specified. So you want. So this is the x1. So the x1 is actually not here. There's an x2 and an x3 coordinate. Yeah. So you also need to know where your coordinate system originates in order to use these coordinates. Yeah. And then you can specify this function. This is again given a velocity, and this velocity is in x direction. So as I told you, this is a scalar. You can also specify a vector, but now since it's a scalar, we have to tell the boundary condition in which direction the scalar applies. And this we do by setting the x value to true and the others to false. We give this as a function, and we say that this starts applied from time step 0 and runs to infinity. So, and then we set this, the algorithm to velocity interpolated. So we actually can have off-grid velocity boundary conditions. This is not important here, but it may be important if you have, for example, a turning wheel or something, yeah, that you want to use. So, on the outflow, we use a kind of pressure boundary condition which is different from the anti-bounce back that we have discussed here. So this is a pressure boundary condition using the non-equilibrium part. I'm not going to explain this, so there are different boundary conditions obviously implemented here. Then again, we use the K17 compressible Navier-Stokes equation, and we have to set the data structure for our boundary condition. So usually in the input file you'll always see this here, because this is now using boundary conditions that, even though they are all tri-node boundary conditions, all of them need a node, yeah, a node where they can be applied. And sometimes we have we have the problem that we don't have nodes where we can apply these boundary conditions. So then we need thin wall boundary conditions. So for example, say you want to simulate, you would like to simulate a sheet of paper, yeah, somewhere in the fluid or moving through the fluid, yeah. So then this would be too thin in order to, so it would have nodes on both sides, yeah, and not be directly on any node. So in this case, we would have to implement a different data structure, yeah. So in the normal case, we always use this one. So you always see this one. Then, yes, there's something that's called a metis visitacet. This is, I'm not going to explain this in detail, but this metis is a library that does domain decomposition. So this is now not important for us when we run this on our desktop or laptop, but if you do this on a distributed systems where you have many MPI processes on different computers, then the domain has to be split up. And in not doing this by hand, we have here a library included, yeah, that does this for us. And when we have this distributed system, by the way, this also means we're writing out distributed files. Yeah, writing out distributed files means if you read these files. So, for example, if you open these files, yeah, so you always you want to read this collection. Yeah, so in this collection, first of all, there are all the time steps in it, and it's also combining the different, the different files of the different domains. Yeah, so I mean, the software is usually supposed to run on supercomputers with many different compute nodes. So internally, there would be OpenMP parallelization on one node, and then there's MPI parallelization across the nodes. Okay. So yes, we have to attach. Okay, so there's some potential way to restart, but I'm not going to talk about restart now. Regarding the cylinder, now we would have, for this thing, we would have two options. Namely, we can simply take a primitive generating the cylinder, but I wanted to point out here that we can also use an STL file. So the STL file, this is now simple because it's just an STL file of the cylinder. So when we when we look at the cylinder and we do it as a wireframe, then we see how the cylinder is implemented, right? So I have another cylinder here. Let me see this other cylinder. If we do a wireframe here, okay, so this, they look pretty similar, even though the one has been generated from a primitive. Yeah, so okay, it was a primitive, and then a triangle net was written out for this, and this cylinder is originally this is originally in STL. So actually this cylinder is not necessarily smooth. It is only as smooth as this triangle mesh is. Yeah, it's not really curved, right? But this is due to the actually, if you want to have really good resolution for your boundary layer, you should use primitives, because primitives actually have curved surfaces. Yeah. So for example, when we want to simulate this track crisis on the sphere that I've now shown twice, then it's actually important to use a primitive sphere instead of a STL of a sphere, because the STL does not give you a smooth surface, and this disturbs the boundary layer, and you actually get the wrong result. Unless, of course, you use a very, very, very high resolution sphere, yeah, which then takes a lot of time to actually discretize. Right. So now I've commented this out. We could simply generate the cylinder like this. And the other way of doing is generating the cylinder and then saying the cylinder should be read from the mesh from STL binary file. There is this STL file. The false means remove redundant nodes. So this is now not done. And this STL file is actually specified in the input file here. Yeah. So okay, so they are read and discretized, and then there is the no slip adapter is added to this. So the no slip adapter that we have specified before, yeah, set boundary strategy, so it uses interpolated bounce back. Okay, so see whether we are new start or not. There's some logging going on here, and again we need the bounding box, and we specify the bounding box now starting from 0 and going to L1 to L2 to L3. So this is basically the box that we have here again, and here we generate this grid, which should not be called cube, because in this case it's not a cube. Yeah, it goes from the minimum to all the maxima. And the blocks, as we have said here, so the block nx, the size of the block, is also specified here and is now used to set the block dimensions as block nx1, nx2, and nx3. Then we do all the walls. So the walls, again, if we go to if we open the files, go once up, there is geometry, and the geometry, for example, let's see, here's an add wall set max. Set max would be that here. So you see, this is a boundary for this. For this is our mesh here. Let's put this boundary here in wireframe. So this boundary is a little bit larger than it needs to be, yeah, but better too large than not. So it's everywhere where the lattice nodes or the domain cuts or touches this boundary here, the boundary nodes are set alongside the surface, yeah, and we have these kind of objects all around this. And here we'll have, let me see. Right, so there's simply walls. There's simply walls to all these sides and a velocity boundary condition in the inflow and velocity and pressure to the outflow. So for example, Z min is attached. Okay, so it's first generated and then it's attached here, the no slip boundary for this 4 walls around it, and the one at the inflow, which also has been generated, I think. No, it's not. It has not been generated. So it's generated. So where is it? Inflow. Yeah, it's here. Inflow. Yeah. So the object for inflow. So we produce a box. Yeah, where we want to specify our inflow. We set the coordinates of this box and the size. And then we specify for the inflow that we want here this velocity boundary condition. Here we always set the no slip. Here we set velocity, and here we set the density boundary condition at the outlet. Okay, then we add all of this, we write these guys out, and then we come to the refinement. So what I did here and what killed my simulation a little bit, because it's now getting too slow, is I set refinement level 2. Refinement level 2 means we go back to seeing the slice. Why is the slice not visible? The slice is here. So, for example, the slice, or what we can also do, we write out the blocks. Okay, we write out the blocks. So the blocks are all of the same size. Yeah, but they don't have a unit aspect ratio. So they are less long, say, than they are wide, yeah. And now we have specified that we want to have 2 refinement levels, and not here. We are here. So. Refinements 2 string. So we specify that let me see, we specify a geometry for this. Kernel block visitor unified. So let me see, I have to go again to I kind of lost the position where this refinement was. Helper, set blocks, geo, restart, set connectors, interpolator. Where was the Okay, let me see where we specify cylinder, cylinder. Cylinder, too many cylinders in it. Refinement cylinder, okay. Yes, so we have to specify where we want to refine. And this, in this particular case, is done through what we call here the refinement cylinder. And this refinement cylinder is a structure that we've now put around this. So this does not necessarily have to look the same way here, and there's always a relatively large halo around this, yeah, because it cuts into these different blocks. And it will surround, so first of all, it will refine this surrounding area here. So we always leave enough space that there is transition between them. This is why you see here a relatively large space in between this, and why you actually don't see. So this now came out all like, you know, even though we refine a cylinder, yeah, it all came out like a rectangle, because we have this halo that we put around this, yeah. So we use this cylinder as specifying where we want to have the refinement. So for example, if you, rather than wanting to refine exactly only the boundary layer, but you're interested in the wake, you would, for example, use a geometry here on this side, saying that you also want to refine this area around here. But this has not been done here. We just refine in the boundary layer. So this specifies the size of this thing. This has been done here, and further up, and somewhere we call the grid refinement node visitor. So now you see how badly prepared I am. Where do we have seen this before? Interpolation, e-processor, Z connectors. So okay, we need to specify these connectors that do the interpolation from one grid to the other, and there are different possibilities, and here we use this compressible offset moment interpolator, meaning that this distinguished from incompressible. So when we use, so you should use if you use a compressible kernel, you should use a compressible interpolator, yeah. Offset is something that we have not talked in the lecture today, but the idea behind offset is there is a possibility. I mean, you have a boundary somewhere, someplace, and you have lattice nodes that you want to interpolate, but you cannot interpolate them because they have the boundary on one side. Then what you do is you use an interpolation cell that is next to this boundary, yeah, and from this you extrapolate towards the boundary. I was very skeptical when before we did this, whether this would work, because it's a pure extrapolation. But due to the case that we are extrapolating toward a boundary, and at the boundary the velocity is small, or actually should be zero, this extrapolation actually works very well. Yeah? Or, I don't know, sufficiently, right? At least it's not going unstable. So this is, and that this is now not covering this. This is what we call this offset, and this goes into the name that we have here, an offset, compressible offset moment interpolator. Right, so this has to be given the viscosity and yeah. So, right, I somehow I missed the point where they set the refinement levels. I've seen this as a level refinement cylinder. If refinement level, okay, yeah, this is where it's set. So if the refinement level is larger than 0, so if it's 0, you don't do anything. But if it's larger than 0, then we hand this refinement cylinder, this is the object that I've shown you in Paraview, to the refinement helper and tell the refinement helper how many levels it should refine, and then we tell the refinement helper to run the refinement, and then we do we write this into the logs. Yeah. So this is the place where actually the refinement is done here. Okay, and then there is also in this particular case, we also want to measure the forces. The forces is, so the forces is calculated by an observer, by a simulation observer. We have again the right macroscopic quantity simulation observer. This is what you usually do. This is, you're writing out your Paraview files. So these are the macroscopic quantities. They are put into an observer, and the observer is added to the simulation. And in addition to this, now we also want to have to calculate the forces on this particular object. So we have a calculate force simulation observer. This observer, so this also needs an output file. It writes a CSV file that you later can open in whatever, Excel or whatever you like. Yeah. This, because it calculates the forces, it needs an area for which we calculate the force. So this is the radius of the cylinder times its length. This is the specified the area, and also this is a scaling for the velocity such that you actually get the CP value out. Yeah, if you want to calculate the CP value, you have to divide by 4 times. I mean, by potentially this value and the force and the area. So you calculate the force, and you have to specify for this force observer where it calculates the force, and for this we add the object, and the object is the cylinder. Yeah, so it will now calculate the force on that cylinder. Okay, and then usually they need to be set to the specific time steps that where we want to have this output. So, and as I said previously, we generate the simulation, and to the simulation we add this different observers. So one observer is the performance observer, yeah, that calculates the number of lattice node updates per second. Yeah, so this is not always done necessarily. If you don't want to know this every time, you don't need to have to add this observer. Here we add the force observer. This is something that was, for example, yesterday we didn't do this. And we add the output observer, so the right macroscopic quantities, and also the restart observer is also an observer. So this will be triggered usually only at either very far away, at specific time steps, or at the end of the simulation. Yeah, this will be triggered and write out the entire information so that we can restart the file. Okay, now yes, and this is then the rest is, I think, the usual part. Okay, now we can specify to run this, for example, a little longer. I don't know. Let's save this. Now I've turned this again to run for a Reynolds number of 20. Now I don't know whether this is going to kill the recording, because this is now taking 8. It is. Can I make this? No. Does this go larger? I don't know. Maybe. So okay, everything. So there's one process. So there's only one MPI process because we are running this only on one computer. But there are 8 threads because we are running this on this 8 cores here that we have. So first of all, we have to generate our grid, and then we would usually have to wait, I guess, something like 3 minutes for this 100 time steps, because we have this very, very refined grid around the cylinder. Okay, now in my computer is now actually heating up a little. Are there any questions? So maybe, you have to. So the questions about these things will of course come up when you get hands-on. But within this 2 weeks, we didn't have really enough time to do the coding and then also going into depth with this here. But yeah, you are encouraged to download this and try a few things out. Maybe we'll wait until we get the first write outs. Well, I think usually it should take some 3 minutes, but since now Zoom is working in the background, it will be potentially much slower. Okay, we can have a look here. So it's taking up 1.3 gigabytes, I guess, in memory. And yeah, all of our compute power. This makes even Zoom go 2%. Okay, so we have 8 million node updates per second in this. The number of updates goes down when we have more refinement levels, because the interpolation also does a lot of work, right? Now we have One thread here has 1 million node updates per second in this case. Now we've written out, we've basically overwritten the first time step. So let me go to the beginning and see what we can see here. So this is, let me remove the refinement cylinder and let me remove the block grids. And yes, so here you go. Maybe we put this other cylinder to surface. Yes, so, oops. Now this is after the first 100 time step. Again, we are at very low Reynolds number 20. So we are using absolute overkill here with 2 levels of grid refinement. This would work without the grid refinement, but this here for demonstration. Okay, now this is, let me see, how long did we take? 20 minutes. So it was something like 2.5 minutes. 2.5 minutes until we get the next time step written out. Yeah, and maybe we'll just look at this because this is not so far away. I mean, one thing that you have to know, we have this 100 time steps. These are the 100 time steps on the coarse grid, right? So we have acoustic scaling here. So when we have 100 time steps here, we do 200 time steps here, and we do 400 time steps on this grid. So this is very different from what is usually done in control volume methods, where you have one global time step for everything. So the good thing here is that actually in the coarse grid you don't need to have such a fine time step. In a control volume method, your time step is always defined by the smallest element that you have. Yeah? So this is a kind of an advantage that we have here, that the time step on the coarse grid is never defined by the time step on the small grid. That this can always be avoided. What you also see here is what we were discussing before, is this overlap region in the grid. Let me go try to remove this. So you see, this is exactly what I've drawn before. Yeah, so we have this node being recovered from this cell, and these 4 nodes being recovered from this cell surrounding it, and then there is the small overlap. By using this small overlap, we avoid to use any interpolation in time. Yeah, and the same thing is repeated here at the next level again. So we may have 32.6, so we would have another minute before we get to the last time step, and if then there is no more questions, then we see on the program tomorrow. So tomorrow I am talking about a few more practical things on implementation. Yeah, so what you have to actually watch out for in order to get this efficiently and accurately implemented. And because we have only one session tomorrow, I see that we are scheduled to start at 9 o'clock, right? So tomorrow we'll start from 9 o'clock. We have now gotten the third time step here. So let's just go to the third time step and maybe looking at this in surface again. No, wait, this is the wrong surface. So we've now seen at a very high resolution, very low Reynolds number flow. This is usually not what you do, right? So this was after 100 time steps, 200 time steps, and 300 time steps. And we would have to wait a little longer to see the to see this to come. To a steady state. So actually, I increased this resolution to a ridiculously high value for this low Reynolds number. This is why we have to wait so long. We could do this potentially much quicker, yeah, if we instead went back here and, for example, used only one refinement level. Yeah, potentially this makes sense. Closing this and running this again. So now we are obviously using kind of less memory. Okay, we are only using, yes, much less memory, obviously. Where are we? Here. So actually, it's supposed to write out how much memory it uses. But we are still in the simulation started. Yeah, here. So it's only. It is, what is this? Almost only a quarter of it. Yeah. So most information is always in the highest resolution, obviously. So, okay, then it takes only 22 seconds in one time step, so it's much quicker. Let us see, it has overwritten this. So, for example, now we get wireframe again. So if I go back to my first time step, I only get this grid here. It's also loading much quicker. Yeah, and it only takes 26 seconds now. So I can go already to the next time step. The quality of the solution will be as good as this because we were overdoing it completely. We see time step 3. So this is where we previously had to wait, like, what was it, 10 minutes or almost. Okay,